As we start with a review of chemical activities 7 and 8, we recognize that the wave function psi is made up of 3 compartmentalized functions. We have the r function, which is a function of the radial distance, the theta function, which is a function of the north to south angle, and we have the capital phi function, which is a function of the equatorial angle. We recognize that this latter part is equal to the wave function y, which is also a function of quantum numbers L and M, and this is the spherical harmonics. And we've also recognized that we have this new radial distribution function, and that function is a polynomial in R multiplied by an exponential that's e to the minus r over 2a naught for the hydrogen atom. But let's for a second ask ourselves what the operator was, and we'll think about the mathematics of this. Well, we can make the Hamiltonian operator. How do we make that Hamiltonian operator? Well, we have a kinetic energy piece and we have a potential energy piece. Of course, the potential energy, when we thought about Cartesian coordinates, that kinetic energy was equal to p squared over 2m, and we recognize, at least for the momentum in the x direction, linear momentum, the operator was equal to minus I h bar di by dx. And of course, when we consider all the momenta in x, y, and z Cartesian coordinates, we would build a Hamiltonian operator that was equal to minus h bar squared del squared over 2m. In this case, we've got the mass of the electron that we care about, so we'll retain the mass of the electron. And a quick reminder of del squared. Del squared is simply equal to di squared by di x squared plus di squared by di y squared plus di squared by di z squared. And this was in Cartesian coordinates, but of course we recognize that there is a format for del squared in terms of the polar coordinates, the spherical coordinates, and we'll come to that in a second. Of course, let's remind ourselves what we're trying to do here. We are going to plug all this into the Schrodinger equation. So we remember from our rules that we describe the system classically. We build our classical expression, in this case of energy, as I circle the kinetic energy here in the picture. And then I substitute in quantum mechanical operators. That allows me to get a new quantum mechanical operator, at least for the kinetic energy. I'm also going to get a quantum mechanical operator for the potential energy, and when we add those two together to get the Hamiltonian operator for the total energy, we recognize the Schrodinger equation as being that eigenvalue equation, and we hope to be able to pull out a definite value for the energy when that equation is solved. So let's for a second remind ourselves of del squared for polar coordinates, spherical coordinates, and that's equal to this expression. We can also recognize that the angular momentum operator squared is equal to minus h bar squared, as shown. And so finally, we can rewrite our expression. We can rewrite our Hamiltonian operator in the following way. Along the way, we can make this substitution. And from that, so this is our revised form of our Schrodinger equation. So let's make some simplifications. We can multiply throughout by r squared and by 2me, and we end up with in fact, I made a mistake earlier. Let me go back and correct that. The r squared is actually on the denominator. Let's again try to simplify and collect these terms together. So a hard part here is to keep track of the pluses and minuses throughout, and notice that we've got a potential. So I've replaced the minus e squared over 4 pi e naught r. I'm simply replacing that with a term that's I'm calling v, which is the potential energy, again to simplify things. And now I'm going to further factorize this equation. So we end up with this final version of the Schrodinger equation.